You'll probably notice that the chapters are out of sequence. And that's because the materials that we need for chapter 6 and 7 and on down are better understood if we get the concepts in chapter 8 in hand. So I don't know what possessed the authors to put them in this order, but I thought chapter 8 was better done now than later. So we'll look at that. Chemical composition. And then we'll get into, in fact, I put chapter 15 out of order too. It comes later. But as far as the next exam goes, chapter 8 is the only material we're going to cover. Let's see here. There we go. So we're going to start off with counting by weighing. First of all, what do we mean by that? Right? Can you count stuff by weighing it? If you just weigh something, there's no way you can count what's in it. Say if it's made up of lots of individual parts. Say a jar of marbles. If you just weigh it, there's no way you can say how many marbles are in there. The other piece of information you need is how much does each marble weigh? If you know that, then you can figure out how many marbles are in the jar based upon the weight of the jar or the weight of its contents. So that's the concept. If we know the average mass of the particles in a collection of matter, then if we get the mass of the matter, then we can convert that into numbers of particles. And that's based upon dimensional analysis. I'm sure I said it earlier. A lot of and what I mean by that is unit conversions. A lot of what we do in chemistry can be accomplished by unit conversions. You just have to be sure that you've got the right conversion factor. And that takes a little knowledge about chemistry to do that. So why would we have to count by weighing? Well, until recently, that's the only way we could get a handle on the number of particles in a mass, the number of atoms in a mass, was by weighing it and then deducing how many atoms are contained there. Now, of course, we have instruments that process so fast and are so accurate in their measurements and their approach that they can count individual atoms. We have instruments that'll do that. But for most of us in chemistry, we don't have access to multi-million-dollar pieces of equipment to do that. Besides, it takes too long. So we still count by mass. So instead of marbles, let's say we have a jar of jelly beans. And to begin with, we know that there are 1,000 jelly beans in that collection. And we also know that not all the jelly beans have the same mass. There are slight differences. So let's say we take a sample of those 1,000 jelly beans and we find the mass of those 10 jelly beans. Then if we want to know the average mass of a jelly bean, we divide the total by 10. Okay, so here's an example. This is a fabricated data set. There's the masses of each jelly bean, and you see that there is some variation in it. Right? The precision's not too bad. And then we say, all right, what's the total mass of the jelly beans? We add them all up, and it turns out it's 50. And then we divide by 10, and that gives us 5.0 grams per jelly bean. So we could say that whole jar of jelly beans should weigh something close to 5,000 grams or 5 kilograms. Okay. Let's see, did I say enough about that? Let me back up. This is the process here in this white inset for getting that little piece of information we need, right? A conversion factor, recall, is an equivalence. So we're saying that 1 jelly bean is equal to 5 grams. That's what we need, right? 1 jelly bean equals 5 grams. So if we have a mass of anything, X grams over here, then all we have to do, and that has to be mass of jelly beans, of course. Then we put the grams on the bottom and the jelly beans on top. Grams cancel, and we find out how many jelly beans there are total. Now, that's not what we would call an exact number. An exact number would require that we count every jelly bean in the jar. This is an estimate because 5 grams is an average of the jelly beans. All right. So we have 2 samples that contain 2 different components, A and B. The 2 samples contain the same number of components. If the ratio of the sample masses is the same as the ratio of the masses of the individual components. Let me read that again. 2 samples containing different types of components, A and B, okay? Both contain the same number of components. If the ratio of the sample masses is the same as the ratio of the masses of the individual components. That's a little hard to follow. I don't blame you if it doesn't make any sense. I think that slide needs to be cut out because we're going to take an actual example here and that'll make more sense. Okay, let me go back. Here we go. Now we're going to go back to marbles. If we have a pile of marbles that weighs this amount, and we know that 10 marbles, we pulled 10 marbles out, and we weighed them at 37.6 grams, how many marbles are in the pile? There are 2 approaches here. That gets you to the same location, 394.80. That's the total mass. We need a conversion factor that will cancel grams and leave us with marbles. Okay? You can either find out the average mass, or you can do the average mass in the calculation. Right? We would have taken 10 marbles and found that they were 37.6 grams. Okay? This would have been 3.760 grams per marble. So it's the same ratio if we had done it as a separate step. But we don't need to do that because the calculation will do it for us. Grams cancel. Now that tells us how many marbles we have. Okay. In this green outline box, we did the average mass first. And then we did the calculation. And this is kind of abbreviated. This is harder to follow than if you do dimensional analysis. That's the better way. Now, why would we want to do it this way? The reason is, going back to the average mass of an atom, the way we determine the average masses of atoms is lends itself better to this way, because you're going to have the average mass of an atom on the periodic table. So you don't have to go through the step of taking 10 atoms and weighing them, or 1,000,000 atoms and weighing them. It's already been done for you. It's on the periodic table. And I'll show you how that works shortly. So we calculate that there are 105 marbles. Now, hold on a second. $394.8 and 37.6 times 10. Okay, so that comes out to exactly 105. But suppose every measurement, remember, has uncertainty. So let's suppose we had measured the mass here, or the mass here was a little off. Say 3.73 grams. 3.73 grams is our average mass of marbles. Then we would have come up with 105.84. If this had been 3, 105.84. Now, you can't have a fractional marble, can you? No. So, for practical purposes, you would have to round that to 106 to give you a whole marble. And that's what we do with atoms too, right? If we have some uncertainty, then you have to make a decision. If you're looking for the number of atoms or the number of marbles, then you have to round to the whole number. Because if you subdivide an atom, you have subatomic particles, and now that's not that same element. So we would have to round. In this case, the problem was devised so that you would come up with a whole number. But practically speaking, that rarely happens. When you do these types of measurements, you come up with fractional numbers. And you have to decide, is this a counting answer, or is it a fractional? Is that okay? So these are some of the decisions you have to make when you're doing these calculations. Okay. So because atoms are so small and they have such very small masses per atom, science has come up with a unit for addressing the mass of an atom in terms of this unit of measure. It's called the atomic mass unit right here. AMU, some texts will even just say A or AU. I like AMU because it follows more smoothly from the name, atomic mass unit. The atomic mass unit itself is worth 1.66 times 10 to the minus 24 grams. It's very small. And as a practical matter, one atomic mass unit is about the mass of one proton. Not exactly, but it's close enough for our purposes. Now, we've discussed isotopes now, so we know what an isotope is. It's the same element, but it has different numbers of neutrons. That means each atom doesn't necessarily weigh the same as the next atom. If it's a different isotope, if it has more neutrons or fewer neutrons, then it's going to have a different mass per atom. So what we end up doing is finding the average atomic mass for an element, taking into account the abundance of the different isotopes. Most of the time, an element will be composed primarily of one isotope. But there are a couple of places, a couple of elements in the periodic table that are more evenly weighted between two isotopes. And I'll point one of those out in just a minute. So we need to take a weighted average. In other words, the average mass of that marble, our theoretical marble, it's not the real marble. It's a weighted average of all the marbles. So if we say that one atom weighs this much and an isotope weighs this much, then how many of them are there? Right? If there's a whole lot of these and just a few of these, then the average atomic mass should be closer to this one because there are more of them. That's what we mean by weighted average. And we weight it based upon the percent abundance of each of the isotopes. Okay, so the next problem is, I told you, the slide showed you the actual mass of an atomic mass unit. But as a practical matter, we need an anchor. We need a starting point. So we have to choose an element, not just an element, we have to choose an isotope of that element and say, this is the mass of that isotope. Everything else is keyed to that one. And as it turns out, we use carbon. For one thing, carbon is very easy to obtain. It's relatively easy to purify. And if you have the equipment, you can isolate isotopes. The particular isotope we're interested in is carbon-12. So what does that mean? That means carbon-12 has 6 protons, has a mass number of 12, and its mass is 12 atomic mass units. Just keep going. That one atomic mass for this isotope is an exact number. It has as many decimals as you want. That's our anchor point. Everything else is key to that one. So there are no other isotopes that will have, that will be exact numbers. Isotopes of carbon, isotopes of any other element will have atomic mass units with fractionals out here. So then why do we say that carbon has a mass of 12.01 atomic mass units? That's because this is a weighted average. Of carbon-12 primarily and carbon-13. Once we know what these this weighted average of the element's atoms are, then all we have to do is find out what the total mass is of our collection, and we can convert that into numbers of atoms. Okay, so here's an example. If this is our weighted average, 12.01 atomic mass units per atom. Okay, that's our average, weighted average mass for an atom. Now, if you go into nature and you isolate one atom, what are the chances that you're going to find one atom with that mass? the probability of finding one atom with that mass is 0. Because this is not derived from a single atom. It's a weighted average. So don't make that mistake. But we can use it because in nature, we've determined the abundance of isotopes. And now all we need to know is that number. And this is our theoretical atom. How many atoms are in that collection? Okay, so if we say, well, actually, we're going backwards. Calculate the mass of 431 atoms of carbon. Right? We don't say what isotope it is, so we have to go back to the weighted average. So we have 431 atoms that weigh 12.01 atomic mass units. Right? So that means that collection of atoms should be 5,176 atomic mass units. Well, you're probably thinking to yourself, well, that can't be. This is the conversion factor, so it doesn't limit the number of significant figures, but that's only got 3. So we should round this one off to 5,180 with no decimal point, right? I mean, if we're, otherwise we spent all that time early in the semester learning significant figures, and now we're not going to use them. Well, it should be 5,180 based upon this. Well, I'll tell you what. There's another argument to be made. This is numbers of atoms. Remember, counting. Counting numbers are exact, so there's no limit to this one. Okay, so we could say 5,176 atomic mass units and get away with it. 75 atoms of aluminum. Okay. Where's our average atomic mass for aluminum? You have to look at the periodic table, right? Hold on a second. Here's one. So where do we find that on our periodic table? Well, you have to find aluminum first, right? Okay, so let me get closer. Get my pointer. Let's see, aluminum is right here, okay? So if you look in the square with aluminum, you'll see that in this one, in the upper left-hand corner, is a number, 26.9815386. That is the weighted average atomic mass units for one atom of aluminum. And we've rounded it off to 2 decimal places, which is usually what I do. In this class, 2 decimal places is sufficient for anything we're going to do. So that's where we got this number. The weighted average atomic mass units for one atom of aluminum is this. So when we do that calculation, we find that 75 atoms of aluminum should be 2,024 atomic mass units. All right. Okay. Here's the next step. Here's the problem. I don't know any balance that will weigh out a sample of an element and give you the answer in atomic mass units. It does not exist. Not in my universe anyway. So we need some way to make the jump between numbers of atoms and actual mass, say in grams. Our balances weigh in grams. And the jump is called the mole. The mole is just a number. It's a number of things. It's a big number of things. Right? It's equivalent to 6.022 times 10 to the 23rd things. That's a mole of things. So if we say 1 mole equals that number, we have a conversion factor, right? It's an equivalence. In our case, it could be atoms, it could be ions, it could be molecules, right? Go outside chemistry. It could be chickens. 10 to the 23rd chickens would be a mole of chickens. Well, 6.022 times 10 to the 23rd chickens would be a mole of chickens. But in our case, we're talking about very small, that atoms, molecules, ions. This is how many it would take to make one mole. Okay, bear with me. The relationship, the definition, the foundation for the mole is based upon this standard carbon. Okay, we know that 12.01 grams of carbon will be equal to of naturally occurring carbon with its mix of isotopes. That mass will be equal to 6.022 times 10 to the 23rd atoms. And that's called Avogadro's number. Now, Avogadro didn't come up with this, but the work that Italian scientist, Avogadro, the work that he did laid the foundations for this concept of counting. So his name was slapped on it in honorarium. Okay, so 1 mole of carbon is this many atoms and is that many grams. So now we have a 3-part equivalence. This many atoms equals a mole. This many grams of carbon equals a mole. This many grams of carbon equals that many atoms. So you can get, let's see, 1, 2, 3. You can get 3 conversion factors out of that equivalence. And that's just examples of the equivalents that are available. Okay, let me wet my whistle. All right. So the beauty of this concept of the mole is that value for aluminum, 26.98 atomic mass units, is for 1 atom. If you have a mole of atoms of aluminum, they will weigh 26.98 grams. So that number in each little box for the element, that mass, it could be mass or it could be atomic mass units. Well, they're both mass, but it could be in grams or it could be in AMUs. But if you have 26.98 grams of aluminum, then you have 1 mole of atoms. Same for all the rest of these examples. Gold, it takes more mass to make the same number of atoms because gold is a heavier atom than aluminum, a lot heavier. Iron, 55.85. Sulfur, 32.07. Boron, xenon, 131.3 grams to make 1 mole of atoms of each of those different elements. Okay. So let's use what we know to find out the number of copper atoms in a 63.55 gram sample of copper. That's copper. So it asks us for the number of copper atoms. So we go and look at our periodic table because we know we're starting with grams. So if we're going to numbers, we need, this is called molar mass. That's the proper term for it. That number, that mass number is molar mass because it's the mass of a mole. So copper, let's see, copper is located right over here, transition element. Okay, if we look on there, it's 63.55. That mass is equal to 1 mole is equal to okay. So we didn't even need a calculator for that one. Okay, which of the following is closest to the average mass of 1 atom of copper? I need to do something with this slide because if you're thinking, we just said that 10 to the 23rd atoms of copper is 63.55 grams, right? So it can't be 1 atom. These are all too big, way too big for 1 atom. So say if you were confronted with this on a test, you would say, well, it's simple. It's got to be that one, right? Because that's the only one small enough to represent 1 atom. And we can do the calculation to prove it, right? 1 copper atom. And this is your conversion factor to find out how many moles of copper. Why do we need to go to moles? We need to go to moles because the equivalence of mass in grams is relative to moles. So we needed to find out how many moles does that 1 atom represent? Well, it's a very small fraction. And then we convert moles into actual mass by using the molar mass derived from the periodic table. And there's your value. So that's the bona fide way to do it. But test-taking technique says E is the only possibility. Okay, calculate the number of iron atoms in 4.48 moles of iron. 4.48 moles. 4.48 moles of iron. And we want to know what? The number of atoms. Okay. In this case, does it really matter that it's iron? No. We've already got a number equivalent for the atoms. We don't care if it's iron. I mean, that's the question, but it could be anything. If we're going from moles to numbers of atoms, we don't need to know anything about iron. We just need to know this one. 1 mole is Avogadro's number. So 4.48 times 6.022 times 10 to the 23rd gives you 2.70 times 10 to the 24th iron atoms. Now we're starting to do calculations. Well, actually, we've done some before, but this is a more practical approach. And your calculator will do these things for you if you set it up properly to spit out the answer in exponential notation. Actually, scientific notation, if you tell it right. And it'll give you that answer in scientific notation. Then all you have to do is say, all right, how many significant figures can I keep in the coefficient? In this case, we have 4 here. That's an exact number. We have 3 here, so we can have 3 in our answer. Okay, a sample of 26.98 grams of aluminum has the same number of atoms as what? As so many grams of gold. All right, we've already proven that 26.98 grams of aluminum is 1 mole. So now you just need to know how much does a mole of gold weigh? So you have to look it up. All right, just look on your periodic table. Gold is a transition element, it's right down here. All right, and we look at that. 196.97. 196 point, rounded off. 197. Okay. So we're gradually finding that the periodic table is chock full of information. Right? We learned symbols, right? You should have learned symbols by now. And then we learned how to use the periodic table to find the number of protons, or use the number of protons to find the element. Now we've got something else to work with, molar mass, that's coming from the periodic table. Okay. This question gets you to thinking about the relative size of atoms. If we have 100 gram sample of each of these metals, magnesium, zinc, and silver. Magnesium, zinc, and silver. All right, we've got 100 grams of each. Okay. Which of the following contains the greatest number of atoms? The relationship here is molar mass. Because if you have a large molar mass, a large mass for each atom, then it takes fewer of them to make 100 grams. Right? So the smallest number is going to be the largest atom. And the largest number will be the smallest atom. So all we need to do is find out what are the molar masses of each one. Right? So I take the periodic table and I'll say magnesium is 24.31. 24.31 grams per mole. Zinc, transition metal, 65.38 grams per mole. And silver, 107.87. 107.87 grams per mole. Okay. So the one that takes the most number of atoms to make 100 grams is the lightest one. Right? 24.31 grams per mole. This is going to be the greatest number of atoms. And this will be the least number of atoms. And that will be in the middle. Well, the example here used atomic mass units, which is fine for the comparison purposes. Right? So this is 24.31 atomic mass units per atom. Let's do it that way. Atomic mass units per atom. There we go. And you get the same result. Okay, here's another one. In this case, all right, let's change things around here. 107.9 grams of silver. 107.9 grams of silver. 70 grams of zinc. And 21.0 grams of magnesium. The question here is arrange them from greatest number of atoms to least. So how do we approach this? They're different masses, right? So we need to find out the relative numbers of these. Now you could go in and calculate using molar mass. You can find how many moles of each one, right? And then compare them. Or if you're trying to get through the test in the amount of time allotted, all you have to do is say, is that less than, equal to, or greater than a mole? 107.9 grams of silver. Let's see, silver is 107.9 grams. This is equal to 1 mole. How about zinc? Let's see, zinc molar mass is, let's see, zinc is right over here on the far right. Let's see, right there, 65.38. This is greater than a mole. And magnesium, we just found it was 24.3, I believe. It's less than a mole. So if we want to put them in order, now all we have to do is say from greatest to least. So the greatest is zinc. And then the middle is silver. And the least is, oh, number of atoms, excuse me. No, that's right. This is greater than a mole. This is equal to a mole. And this is less than a mole. There we go. So here we actually did the calculations. And then put them in order. Now, BAC. So B, A, and C. All right, so this is just a gentle reminder. When you're trying to solve problems that you've never seen before, which is our goal, to help you solve problems. First thing you do is ask yourself, what's the problem? Right? And for homework and exams, you say, what's the question? What is the problem asking me? Right? If you don't know what the question is, you'll never get the answer. So that's your first thing. What is the question? And then you need a strategy for, now that you know the question, you know where you're going, you know what the answer, you know the direction of the answer, how you're going to get there. If it's a very simple calculation, maybe you've got all the information there, you can plug it into a formula and you're done. But life is rarely like that. Most of the time, problems are very complex. So your strategy would be to break the problem apart into smaller pieces that you can fit back together. Once you find the answer to each of the pieces, then you fit them back together, and then you get your final answer. That's more common. And then you check and say, does my answer make sense? I had a good friend of mine at Louisiana State University was a student in the mechanical engineering department. I was in agronomy, crops and soils, and he was in mechanical engineering. And he told me, he said it amazes him. The students, they would all be studying various concepts in a certain engineering chapter. And then they would have an exam on it. And he was amazed at how the students would take formulas from that chapter and then take the problem that was given to them and cram the numbers into that formula without any consideration for whether those numbers were supposed to go in that formula or not. And invariably, they come up with the wrong answer. But they turn it in anyway because they have no concept of reality. Does that answer make sense? Right? If I did a calculation, had information calculated based upon planet parallax and measured the distance to the sun. How far are we from the sun? Well, we know that we're about 150 million kilometers from the sun. Right? We know that from other sources. But if I was asked to do the calculation and I come up with 150 kilometers, right? I mean, the sun would be right on my doorstep. So that doesn't make sense. I did something wrong somewhere. So you do a reality check. Right? Does your answer make sense? Okay. So molar mass, I gave that to you just a few minutes ago. And it simply is the grams, the mass in grams of 1 mole of the substance. And we say 1 mole of the substance because, like I said, it could be ions, it could be atoms, it could be compounds, whatever. The molar mass of nitrogen is 14.01 grams per mole. That's the weighted average of naturally occurring nitrogen collected from our environment. Molar mass of water, though, is 18.02. How do we get that? Well, all you need is the molar mass of 2 hydrogens plus one oxygen. Add those together, 2 times that plus 1 of these, 18.02 grams per mole. It couldn't be simpler. You just take the formula, and if you have 2 hydrogens, then the molar mass of hydrogen has to be multiplied by 2. Because for every mole of water, how many moles of hydrogen are there? For every 1 mole of water, there are 2 moles of hydrogen and 1 mole of oxygen. Okay. Same thing for barium nitrate. We know how to write compounds, right? Barium is an alkaline earth. It has a 2+ charge. Nitrate is a polyatomic ion with a 1- charge. So you need 2 nitrates to balance the charge on barium. Now, that's not a molecular compound like water is. That's an ionic compound. But the formula unit is all you need to do the calculation. And the formula unit says 1 barium, right? 1 barium, 1 mole of barium atoms in this formula weighs that much. And you have 2 nitrogens because of that parentheses, right? 2 times what's inside. So 2 times 14.01 for the nitrogen. Then how many oxygens do you have? 2 times 3 is 6. So 6 times 16 is the oxygens. And you just add them together. Right? Did we add them together? Oh, yeah, here we go. 261.35 grams per mole of that compound. All right. Now, mathematically, this formula is correct. But from my way of thinking, it's a little difficult to handle because you would have to memorize this thing, and you could only use it for that purpose. Whereas if we wanted to say, if we had so many grams of a sample and we wanted to find out how many moles that was, so we have X grams of our sample, then we would multiply it by something that would cancel the grams and leave us with moles. Anytime you see grams and moles, or not just see it, you deduce that that's what you need in your conversion factor, right? To cancel the grams and leave you with moles. Anytime you have the quotient of moles and grams, it doesn't matter if grams are on top or moles are on top. Anytime you see that ratio, think molar mass. So this would be the molar mass. And we would have taken this one and just moved it over here, mathematically speaking, multiply it times that, and that would give us the mass. Although this would have been moles, excuse me. Say if we had moles here. I'm trying to parallel to this one. Moles then. Now we would need grams on the top, moles on the bottom. And then you would have mass of your sample. It's pure math. All right. Let me see. How am I coming here with molar mass? Okay. This is just another arrangement. If you think through your problem, where am I? Where is my answer? And the conversion factor is how I get there. Okay, what's the molar mass of nickel 2 carbonate? In this case, it's like I said early on, if you don't learn the elements, the symbols, you don't learn how to name compounds, then this stuff is going to come back to bite you, because that's a name of a compound, and you cannot determine the molar mass without the formula. So we need nickel, which has a 2+ charge based upon that right there. And then carbonate. So what's carbonate? Right? With a 2- charge. Right? It's a polyatomic ion. You only need one of each, right? So our compound is this. Then you need the molar mass of nickel, the molar mass of carbon, and 3 times the molar mass of oxygen. And that should be coming up here. Here we go. So here is the compound. Here's the molar mass of nickel, the molar mass of carbon, and 3 times the molar mass of oxygen. And there's the molar mass of that formula, that compound. Let's see. Okay. We have equal moles of each of these compounds. Dinitrogen monoxide, nitrous oxide, laughing gas, aluminum nitrate, right? Aluminum has a 3+ charge, nitrate's a -1 charge, so you need 3 of them. And since it's a polyatomic ion, you have to use parentheses. And then potassium cyanide, every murderer's friend. Rank these from least to most number of nitrogen atoms in each sample. So if we put them, it helps to, when you're trying to solve a word problem, it helps to extract information from the word problem and put it in a more recognizable form, right? Word problems are designed to confuse. And if they confuse you, that means you don't know the subject, or you haven't extracted the information from the confusion. So laughing gas and aluminum nitrate, and then potassium cyanide. And the question is least to most number of nitrogens. So we're focused on that, that, and that. If you have equal mole samples, okay, same number of moles of each of the compounds. So 1 mole of this has 2 nitrogens. 2 nitrogens per mole. This one has 3 nitrogens per mole. This one has 1 nitrogen per mole. So if we rank it from least to most, it will be this one, and this one, and this one. So that would be which? This one right here, C. Okay. Now it's getting a little more difficult. More complicated problem. Say you have a 100-gram sample of each of the following. Okay. we want to rank it from the greatest to least number of oxygen atoms. Okay, so this is one of those problems which is not too complex, but complex enough that you need to break it apart into separate steps. All right, what's the question? Greatest to least number of oxygens. So you could say, greatest to least number of oxygens. All right, we're starting off with a 100-gram sample of water, laughing gas, C3H6O2, which is a carbohydrate, and it's probably propionic acid, but you don't need to know that. Okay, so those four compounds, we have 100 grams of each one. Okay, that's all the information that we're given. If we want to find out the greatest to the least number of oxygens, what do we need to do? Well, first of all, we've got to find out how much of each one of these we've got. We've only got masses. If we're going to go to numbers, what's the magic number? Grams to moles. So we need to convert that grams to the number of moles of the molecule first. And then once we know the number of molecules of the whole, we can say, how many oxygens does that represent? So it's a chained conversion. We're going to convert this, each one of these, and this is what I call my Henry Ford procedure, my assembly line. You set it up so that you can do the same calculation for each one. You just need different conversion factors. So for water, we want to convert grams to moles. And that's moles of the compound. The magic number is 18.02. Right? We just determined that. Molar mass of water. How about dinitrogen monoxide? Well, let's see. One nitrogen is 14.01. So we need two of those. And then we need to add one oxygen. (4402). Right? Sometimes you don't even need a calculator. I suspect we will need our calculator eventually. How about this one? Right. 1 mole of that compound is what mass? Well, we need 3 carbons. I'm going to use my calculator for this one. We need 3 carbons at 12.01. Where did I get that? From the periodic table. Carbon, 12.01 grams per mole. And then hydrogen is 1.01 times 6. Okay, add those together. And then 2 times 16 is 32. So I get 74.09. Right. Grams cancel, leaving with moles. And then the last one is carbon dioxide. So carbon is 12.01. And then 2 oxygens is 32. 4401. Okay, so now this tells us how many moles of the compound we have. But the question is the number of oxygen atoms. How many moles of oxygen do we have? What we need is the ratio. Right? More assembly line. So this is moles of compound on the bottom. For each mole of compound, how many moles of oxygen do we have? This one is 1 to 1. This one is 1. This one is 2. And this one is 2. Okay, these cancel. And we leaves us with moles of oxygen. Now we can rank them because moles is a number. All right, so if we divide 1802 into 100, I get 5.55. This is moles of oxygen. Okay. How about this one? 100 divided by 4402. 2.27. And 100 divided by 74.09. I get, oops, I did something wrong. Hold on a second. I just checked myself for reality, and the number I got just didn't make sense. So I'll do it again. $1.35. Oops, what did I forget to do? Times 2. 2.70. And then 100 divided by 44.01 times 2 is 4.54. Okay, greatest to least number of oxygens. All right, greatest is this one. Next is this one. Next is this one. And that one's last. So here we've got, it's hard to see, there's a faint line right in here, the divisor line right there. We did the same thing here as I did here. Cancel grams, leaves us with moles of the compound. And then the ratio of the moles of oxygen to moles of compound. Now, this one goes ahead and calculates atoms, but in order to rank them in order, you don't need that. All you need is moles, because moles represent numbers of. And once we do those calculations, we can rank them. Here we go. Water's number 1, carbon dioxide is number 2, propionic acid, and laughing gas. And that's the order. And if you do it like this, like Henry Ford would, assembly line, then you're less likely to make mistakes, because all you have to do is be sure you set the first one up right. And then the rest of them follow with their individual characters, conversion factors. Okay. Let's see here. How many grams of fluorine are contained in one molecule of boron trifluoride? Okay, that looks pretty troublesome, doesn't it? The question is, how many grams of fluorine? And what we're given is one molecule of boron trifluoride. Boron trifluoride, one boron, oops, this trihydride, boron trifluoride, one molecule of that. And we want to know how many grams of fluorine are there. So we're headed here, grams of fluorine. All right, how do we get there? Well, this is in numbers counting, and this is in mass. So you can bet we're going to need molar mass somewhere along the way. Should we calculate the number of moles of this? Well, actually, yeah, the number of moles and then convert it to grams. But then we would need the ratio of fluorine to boron trifluoride. Right? A simpler way would be, if we've got one molecule of this, how many atoms of fluorine do you have? You have 3 atoms of fluorine. Okay, now we're getting somewhere. How many moles is that? 6.022 times 10 to the 23rd atoms per mole. There you go. Now we got moles. We know the ratio of moles to grams for fluorine. Okay. Moles to grams. So we should look it up in the periodic table. Fluorine, it's a halogen. 19.00. There we go, moles. And that gives us grams of fluorine. All right. So if you divide these out, 3 divided by that is going to be a pretty small number, right? Because this is in the denominator. So when you divide it here, you're going to get a big negative power there, times 19. And so there's 3 atoms of fluorine, right? And then we convert it to moles, and we convert the moles to grams, and we get 9.465 times 10 to the minus 23rd grams. Fluorine in 1 molecule of boron trifluoride. Now, did I name that correctly? I mean, it says boron trifluoride up there, but is that proper? Right? What type is that? A type 1, type 2, or type 3? Boron and fluorine are both nonmetals. So yeah, it's a type 3 naming convention. Boron, you just have to say how many there are. Boron trifluoride, 3 fluorines. Okay. All right, now we're getting more practical. When a chemist is presented with a compound and they need to know something about its composition, they go through a number of steps. First, you go through a qualitative assessment to find out what are the elements in there. And there are a number of ways you can do that. Once you know the number of elements, then that'll tell you how that you can analyze the compound to find out how much of each element there might be in that compound. And it depends on what the element is. Some are easy and some are difficult. Some labs are set up for it and some are not. So you may need a working relationship with a sister lab somewhere that's set up to do that analysis and send them your sample. It's easier to do that than try to do it yourself, just for one sample. But what you end up with, the answer you get is mass percent. What's the percentage by mass of each of the elements in the compound? Now, this example is going the other direction. It's taking the compound, written out elements, numbers of elements in the compound, and determining the percent by mass of each compound, of each element in that compound. And what I just described to you was the other way. You take an unknown compound and you determine the mass percent of each element. Well, it's flip side of the same coin. So let's follow the slides along and say, if you want to know the mass percent of an element in a compound, what you need to know is how are they related? How are each element related? So let's say if we had an element here that's 1, and then this one is maybe 4, then you would take the molar mass of X plus 4 times the molar mass of Y. And that would be the total. So for 1 mole of that compound, you would have a total mass, total molar mass. That goes in the denominator, mass of the compound. If you have 1 mole of that compound, how many moles of X do you have? Well, you have 1 mole of X. The molar mass of X is the mass of 1 mole of X. You divide that by the total, times 100. That's percent of X in that compound. That's the calculated value. The experimentally determined value may not be exactly like that, right? Experimental error. Always got error in any measurement. But this is the ideal. This is the expected value. Right? So let's take an example. Iron 3 oxide. They're kind enough to give you the compound there, along with the name. Right? So Fe2O3 is the formula for the compound. So what's the mass percent of iron in that compound? Well, you got iron, 2 moles of iron in your numerator, but you've also got 2 moles of iron in the denominator. Right? You didn't subtract from the whole to get the denominator. You need the whole. So you're going to find this in both the numerator and the denominator. What else do you find in the denominator? Well, the other elements in your compound. So 3 oxygens will also be there. Okay, so that's your ratio in this formula, times 100 for percent. Okay, so 69.94% of that compound is iron. Now, remember, I'm pretty sure I said this early on, but I'll repeat it. When we're talking about percent of anything, percent is a dimensionless number. It just means parts per 100 parts. That's percent. So it's important when you're given information or when you ask to calculate something, you specify what the parts mean. In this case, parts is grams per 100 grams. So this is often written as percent, mass, mass, or percent by mass. Okay, when you're specifying what percent means. It would be great if modern science has come along earlier, then this percent would not have had to been grandfathered in. So we're just having to deal with it now. Under ideal circumstances, we never would have had percent. It would have been actual values in the ratio. But since we're stuck with percent, we have to deal with it. So if this is 69.94% iron, what would be the oxygen? Do you need to go back and calculate the oxygen? Well, no. Oxygen is the only other element. So it's 100 minus 69.94% would be oxygen, right? What would that be? 30.06 would be percent oxygen. All right. Morphine, derived from the opium plant. I've never been on morphine. My wife has had it after operations. They give it to you to ease the pain, post-op pain. And they'll even put it in a drip, let's say. In other words, you've got an IV with Ringer's saline solution flowing through it, or lactated saline, lactated ringers, they call it. And then they'll have another line in there with a smaller drip of the morphine that's going in. Well, morphine has a chemical formula, and this is it. 17 carbons, 19 hydrogens, 1 nitrogen, and 3 oxygens in that molecule. Now, this tells us how many atoms of each element are in one molecule. So what percent by mass is the carbon? What would we do? Well, what's in the numerator? 17 times 12.01. Right? And down here is another 17 times 12.01. But also 19 times 1.01 for the hydrogens. And then a nitrogen, only one of them, and then there are 3 oxygens. Times 100. That's your percent of carbon in that compound. So there you are. And it turns out that there's a lot of carbon by mass. Right? Now we're talking not numbers of carbon atoms, but masses of carbon atoms in that one molecule. 71.6% carbon. All right. Now, does this formula tell us anything about the structure of the molecule? Nope. That's what's called the molecular formula. That's how many carbons are in there, how many hydrogens, how many nitrogens, how many oxygens. It doesn't say how they're arranged at all. Okay. Let's see, 100-gram samples of each one of these. Highest to lowest percent oxygen by mass. So in this case, we would calculate the percent oxygen just like we did for the other examples and do it in assembly line for each one of these compounds. Highest to lowest percent oxygen by mass. Now the temptation is to say, I bet one of these over here would be more oxygen by mass, right? Because there are 2 of them, right? Probably wouldn't be this one because that molecule is bigger, which would depress the percent. But you don't know until you actually do the calculations. So there's percent oxygen in water, right? 1 oxygen, and there's the mass of a mole of water. I forgot to plug my battery. And then we do the same thing for laughing gas, and then for propionic acid, and then for carbon dioxide, and compare the values. So the greatest percent of oxygen by mass is water. And the next is carbon dioxide. The next is propionic acid, and the last is laughing gas. Okay. Now, looking back to laws of chemistry, we know that this percentage of oxygen will always be the same for water. No matter where the water comes from, it'll always be 88.81% oxygen in pure water. Whether you get it from purifying seawater to make high purity water out of whatever source, or if you make it by chemical reaction. Hydrogen gas and oxygen gas react together violently to produce water. It'll be exactly the same percent. no matter what the source. That's the law of definite proportions. All right, so there's the order. That answers the question. All right, so I mentioned earlier that morphine formula, that was the molecular formula. That is actually the molecule of morphine has that many carbons, hydrogens, oxygens, nitrogen in there, in that molecule. But if we go back to the beginning of this discussion, where we're talking about determining percent composition of individual elements in an unknown compound, which is the way it always happens, then can we use that information to find out what that formula is? And the answer is yes, if we have another piece of information. First thing you do with percent composition is determine the empirical formula. All right, I have to define what is an empirical formula. Empirical formula is the simplest whole number ratio of elements in a compound. All right, what does that mean? Well, example. This is benzene. I'm just telling you that's benzene. That doesn't say anything about the structure, so it could be something else. But I'm saying, for our purposes, that's benzene. Okay? What's the empirical formula for benzene? Well, can we simplify that ratio any further? Yeah. If you divide this through by 6, what do you get? That's the empirical formula. Okay? Or let's say acetylene, C2H2. That's acetylene. The empirical formula for acetylene is that. The same as benzene. Okay? So if we use the percent composition of carbon and hydrogen that's given to us by the lab technician, the only thing we can do is say it's this formula. We don't know if it's based upon that molecular formula or this one. Right? At this point, we don't know. But it is a first step. All right. Simplest whole number ratio. So, how are these two related? Right? If we take this one, if we say CH, and then we put a subscript out here as our multiplier, say N. If N is 2, if N equals 2, then we have C2H2. If N equals 6, then we have C6H6. Okay? So we need some way to find out what is that multiplier. That integer will tell us what our molecular formula is based upon the empirical formula. So it's a step-by-step process. You got to find the empirical formula first from percent composition. And then you've got to find out somehow what's the molar mass of that compound by some independent determination. And then I'll show you how to determine, using that information, what that multiplier is. Okay? So here's an example. Let's see, how we doing? We're pretty good along. Let's see, I don't want to have to rush. Okay, so here's the step by step. When you're given percent composition by mass, you can find the empirical formula. Here's the word problem. A gaseous compound contains carbon and hydrogen. That's it. You know it only has carbon and hydrogen. So the bench chemist went into the lab and did some qualitative determinations. What's in this compound? Found only carbon, only hydrogen. Okay. So we know that. Carbon and hydrogen. Okay. Now, the bench chemist went and did quantitative determination. How much of each of those is there? And the chemist came out and said, all right, 83.65% carbon. By mass. Okay. What's the empirical formula? Do we have enough information? Sure. If this is 83.65%, how much is the hydrogen? It's what's left over. So it would be, let's see, 5, 3, 6, 1. Correct? 5 is carrier 1, 0, carrier 1, 0, 9, 10. That's 100%. Okay. Now, how do we find the empirical formula? Well, remember that a chemical formula is not written as a ratio of masses. It's written as a ratio of atoms, or in our case, moles. So when we find out the formula, right, the ratio is going to be number of moles of carbon to number of moles of hydrogen for each mole of the compound. So we got to get that somehow, that percent by mass into moles. We got to convert it into moles. But that's not mass, right? It's a dimensionless number. But we do know that it's mass per 100 grams per 100 grams. So here's what I do. Assume 100 gram sample. Now, what does that percent become? If it's grams per 100 grams and you have a 100 gram sample, then this becomes grams. Right? 83.65 grams per 100 grams. That's percent. Now that you've got mass, we can convert that to moles because we know the molar mass of carbon, we know the molar mass of hydrogen. Okay. Grams on the bottom, moles on the top. Okay, hydrogen is 1.01. Look it up. Carbon is 12.01. Okay. This will give us the mole ratio in the compound. All right, so let's see. 83.65 and 12.01 is 6.965. 6.965 moles. And 16.35, enter, 1 is 16.19. 16.188. This is one of those cases where, in order to avoid introduction of rounding error, I keep as many decimal points as I want. And I'll show you why it doesn't make a difference here. Significant figures aren't as important as having plenty of decimal places. But this is the molar ratio of carbon to hydrogen. 6.965 moles of carbon for every 16.188 moles of hydrogen. Well, the subscripts in the formula are never fractional numbers. They have to be whole numbers. So we need a ratio. We have established the ratio as this to this. So mathematically speaking, if I do the same thing to this one as I do to that one, then the ratio is still preserved. Let's say we divide both of them through by the same number. Let's divide this one through by 6.965 and divide this one through by 6.965. That one's obviously 1. So what is this one? Let's see, it's still in my calculator. And let's see, I'll do that and that. 2.32. So now we're getting closer. One of them is a whole number. That carbon is a whole number, but this one's not. So we need to do something else. What will make both of them whole numbers? We've got to get rid of that fraction. What is this fraction close to? 0.33? It's close to 1/3. So if we multiply both of them by 3, that will give us 3 times 1 is 3. And 3 times 2.32 is 2 times 3 is 6, plus 1 is 7. Okay? And notice that I rounded in my head. It's not exactly 7. I mean, 3 times 0.32 is not exactly 1, but it's very, very close. And we have to round because we can't have a fraction of an atom. So the empirical formula is C3H7. Can we reduce it any further? No. Those are both prime numbers. You can't divide them by anything that will reduce them further. So that's our empirical formula. Okay? That was the first step right here. Next, determine the number of moles of each one. Right? There's moles of carbon. And, see the discrepancy here? They used 1.008. They went up to 3 decimal places, whereas I rounded off to 2. So we divide through by the same number. They got 2.33, I got 2.32. We're going to round anyway. So multiply by 3, and there's your empirical formula. Now, that's not the molecular formula. In other words, this doesn't guarantee that the molecule will only have 3 carbons and 7 hydrogens in it. It could be a multiple. It could be any multiple of that. If n equals 1, then yeah, that's the formula for the molecule. If it's 2, then it'll be C6H14. Okay? What we need is the molecular formula. Well, we need the molar mass of the actual molecule. Okay, so with this percent, keep going. There you go. Right, we have the empirical formula. Now, by some independent means, we have determined that the molar mass of that compound is 86.2 grams per mole. So, whatever n is, the molar mass would be 86.2 grams per mole. Okay? Well, what is the molar mass of that formula right there? The molar mass of that formula would be 3 times carbon. Right? So that's 36.00. And then 7.07 for hydrogens would be 43.07 grams per mole. This is the, sometimes I call it molecular weight. I know that's not true because it's not a weight, it's mass. But this one I would call the empirical weight. Or the molecular mass versus the empirical mass, whatever you prefer. notice that if we ratio this one is like that. If we multiply it by 1, it should be that. But it's not. If we multiply it by 2, it would be that. So this is N. The ratio of the molecular mass to the empirical mass gives you the value of N. And sometimes, based upon experimental error, you may have to round the value. But if it's going to be close to some whole number. There's your ratio. That gives you the multiplier. So the molecular formula is actually C6H14, which is hexane. Okay. How are we doing on time? We've got about 25 minutes. What do we have here? We're told that adipic acid has 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. So you're given all the masses for these three elements that are in that formula. What is the empirical formula? Okay. Again, we assume 100 grams because we're not told what the mass of the sample is. If you're told the mass of the sample, then you can use percent to determine the mass of each of the components. But if you're not, assume 100 grams, that's the simplest way. Then you've got 49.3 grams of carbon right here. And that is equal to 4.105 moles of carbon. Right? We set up our Henry Ford assembly line, and this is what we'll get from each one. Hydrogen will be this many moles of hydrogen and this many moles of oxygen. Right? We just divide by the molar mass of each one. Then we want to get the ratio of these. So how do we get the ratio? Start working our way towards whole numbers. You take the smallest one and divide it into everybody. 2.7375 divided into each one of these. Right? So oxygen will be 1. 2.7375 into 6.845 is about 2.5. And then 2.7375 into 4.105 is about 1.5. So how do you get rid of the fractions? Well, a half times 2 is 1. Right? So multiply the whole thing through by 2. You have already established the molar ratio here and here, right, for that empirical formula. So anything you do to it, multiply it by something, divide by something, the ratio is still the same. So times 2 would give us a ratio of 3, 5, and 2. 3 carbons, 5 hydrogens, and 2 oxygens. And our formula would look like this, our empirical formula. Then, of course, you ask yourself, can I simplify it any further? Well, 3, 5, and 2, they're all prime numbers. No, you can't simplify it any further. Okay, how about the molecular formula? If you know that 3, 5, and 2 is the ratio of carbon, hydrogen, and oxygen, then what's the molecular formula if you're given the molar mass of the compound? The molar mass of this compound is 146 grams per mole. So what do? You find the empirical mass. What is the empirical mass for that formula? And divide it into the molar mass of the compound. And that gives you your ratio, that N multiplier. Okay. 73.07 for this. That looks like it's about 2, doesn't it? 7307 into 146 is about 2. So now the multiplier is 2. The formula is C6H10O4. And that is adipic acid. Adipic acid is a fatty acid. Okay.